Welcome, everyone. My name is Mark Hughes, and I'm part of the team at Advanced Assembly in Aurora, Colorado. I know it's a lot of, let's call them unusual times that we're all experiencing right now, and I'd just like to thank you all for taking the time out of your busy days to join us. If you need these slides at the end of the presentation for any reason, feel free to reach out and we'll provide them to you. It's not a big deal, and there's going to be a lot of information coming at you. Joining me today is Greg Zeraldo. Yes, Hello. That Greg Zeraldo. I know what you're thinking. Some of you guys have the Greg Zeraldo action figure. Yeah, it's that Greg Zeraldo. Anyways, Greg Zeraldo is the Senior Director of Operations at Advanced Assembly, and he's taken our idea of quick turn to a whole new level. So Greg, maybe introduce yourself and tell the folks a little about your experience.
Yeah, thanks, Mark. I appreciate it. Yeah, my name is Greg. I'm over operations over at Advanced Assembly. We are a quick turn PCB assembler based out of Aurora, Colorado, which, if you're not familiar with the geography of Denver, Aurora is the field out back behind Denver. So we're about a stone's throw away from the airport, and we pioneered the way on what way that we build circuit board assemblies. So whether it's in a matter of hours or days or whatever really you need for your project, we're able to do it. So glad to be here.
Hey, and we're happy to have you. So today I've asked you to talk to us and revisit your presentation from PCB West last year. Was very popular on heavy copper. So I was hoping maybe we could kind of tag team this so I don't have to, I want to not stress that silky smooth baritone of yours too much, as we go through it. People have questions. Go ahead and use the question and answer box rather than the chat if you can. It'll just kind of help us manage things. We've got two people working Q&A, and that'll help us get things going. So as we go through this, I'll maybe take a look at material properties, and then maybe we can work together on design considerations. Fabrication's all yours, as is assembly. And then maybe we can go back and forth on tips and questions. Sound good?
Yeah, absolutely. I think the best way to do this is, just to provide kind of a different type of content for the people out there listening too, to where, just general blasé information and everything like that gets a little boring. So obviously with everybody being at home or out of their office right now, let's mix it up and make it interesting. So here we go.
All right. Maybe pepper in a dad joke or two. Hey, since there is
I'll leave that to you.
Hey, okay. I'm going to start with one, Greg, just to kind of break the ice, make people feel a little more comfortable. Since it is a medical emergency, right? So I went to the doctor the other day. Doc, man, I broke my arm in 2 different places. You know what he told me? Don't go to those 2 places. That's right, folks. Don't forget to tip your waiters and waitresses.
Do you want to see yourself out, or?
Make sure you try the gefilte fish. All right. So copper is pretty unique in the metals that we use for PCB fabrication. It has excellent electrical and thermal conductivity characteristics. In fact, it's second only to silver as far as that goes, and not by a large margin. But silver is pretty dang expensive and somewhat hard to work with, so copper wins out. Some other materials that you see in printed circuit boards, things like gold, are ridiculously expensive and not all that easy to work with. But gold's got the positive benefits of it doesn't tarnish. There's no oxidation. So the resistance on day 1 is the same as the resistance on day 30. Maybe not at day 1,000, but it's still pretty good. And we sometimes see aluminum used too. Another material that we use, although only usually a few atoms thick, is nickel. But I mean, of all these things, copper's a pretty good balance of machinability, of price, of thermal and electrical conductivity. So it usually wins. But there's some drawbacks with some other materials that we have in printed circuit boards. For example, the coefficient of thermal expansion. You want this one, Greg?
Yeah, so, basically with this, at the end of the day, without getting too into detail on the technical side of it from my aspect, if you want to dive into a little bit more of that, you're more than welcome to. But guys, really at the end of the day, your laminate and core materials, your pre-pregs at the end of the day, they're going to expand at different rates than your copper is. Okay, so your copper plating, whether it's on the surface or in your barrel and your via, if you're going to be thermal cycling, if you're going to be putting these through thermal stress, at the end of the day, they are going to expand at different rates. So what you need to be looking at is really these, like if you're looking at a z-axis expansion, this is where really trouble can set in, because that core can expand much more than the copper can. So if you're putting additional stress into that from a heavy copper standpoint, and your material is not set up to be able to handle that expansion rate, you're going to run into a whole mess of problems. The biggest ones that you're going to be running into is from an inner layer connectivity standpoint is a via failure. And so basically, if your plating isn't done correctly, your board is going to fail. The images that we have put up are 3 separate images of what you could potentially be set up against. The image that's on the far left is basically a stress crack within that plated hole. And so between this image and in the middle image, what can actually happen with that is that depending on the thermal cycling that you're doing with this can actually expand and contract that. And so you might have an intermittent open, depending on how you're testing it, or you actually might show that through an electrical test that everything is fine, but then you go to deploy it to the field, it sees its thermal stress, and then this thing is going to go blow wide open, and then you're going to see your failure. So, at the end of the day, pre-planning for these things and understanding what your material properties are, your copper thickness, and really understanding what this board is designed and going in to do. I mean, is it as a payload to go into space? Is it for downhole drilling? Really understanding what its final use is going to be critical to life on your next steps. The third picture real quick too, before we go on, the third picture from there is actually the complete separation from the inner layer. You'll see that actually there's a hard designated line across that via where there's no longer connectivity. So at one point that was connected, and then that circuit is now broken. So this would be an immediate failure, whether it was latent or immediate. It's just no longer functional.
Huh. All right. Hey, Greg, would that be one of the reasons why I had a board fail? I don't know. It was probably 3 or 4 years ago now, but the dang thing would just all of a sudden just start doing endless power on resets after we used it for about an hour or two.
Yeah, absolutely. And so, I mean, it's just honestly, it's the board cooling, contracting, heating up, expanding again.
Yeah.
And so it's basically turning itself on and turning itself off without any actual mechanical change to it. So short answer is yes. There's a very good chance.
Interesting. Huh. All right. So when we're doing stuff like this, really in times past, I've not worried about it. You kind of go find your boss and say, hey boss, this board's going to get hot. Tag, you're it. I've never really had to do any of the thermal design myself, thankfully, because I feel somewhat ill-equipped to do it. But I know that you can simulate, and I know you can estimate, right? You can simulate with computer programs, or you can estimate with equations and icky math. My understanding is simulations needed when you have airflow, right? Convection that you're depending on, and movement, maybe forced air convection. You're doing things like downhole drilling, or you're doing components that are going to get really, really, really hot. It helps to throw that into a program like ANSYS, or maybe even SolidWorks or Autodesk, Mintra Graphics. I have played with SimScale for the computational fluid dynamics, but nothing really past that. Do you happen to know how accurate you can get with these simulations, or do you have any tips that I could go through?
So as far as the accuracy goes, I mean, it's realistically, again, it goes back to your original design and what it's going to be going into. As far as if you have something that is a critical product, it's lives are at stake. It's higher level than something that you're kind of doing initial testing on. Simulating these products through software is going to be an absolute necessity, because you're going to need to get real world data of exactly what you're seeing. You're going to need to be able to simulate and see potential thermal areas and hot spots on your board when you are going through the design and manufacturing and assembly process with it. if you don't have this visibility on it, you're going to go end up powering up your board and through functional testing and all those fun things, and then you're going to end up just blowing the thing up. You know, so there's a lot of different ways to simulate that. You know, as far as actual like hard data of what you're really going to get out of it is going to be completely up to the design and how you program it. You know, if you want to kind of, you know, go over the estimate side of it, which is definitely kind of a lower level way that you can get data just by derating and everything. But, you know, this isn't something where you want to take a board that's going up on a Falcon 9 rocket and just do basic estimations on it. So you want to discuss that a little bit?
Sure, sure.
Go for it.
So are you referring to the estimations like in IPC 2221 and the online calculators and that sort of thing?
Yeah, you could, yeah, essentially that, and
Yeah.
just the general estimate, calculate, and derate.
Sure. So when I started doing some research for this webinar, and I don't know when we started it, we've been kind of doing this on and off since, what was it, October, something like that.
Mm-hmm.
I was looking at the online calculators, and I saw that all of the online calculators use the IPC 2221 standards. Now, the interesting thing about those is that they've been replaced by IPC 2152 standards. Now, ask me why they did that, Greg.
Why did they do that, Mark?
I'm glad you asked, Greg. It turns out that the IPC, don't worry, folks, I'll be here all week. Turns out that the IPC 2221 standards are based off of some math and equations that two researchers back in like the 1950s and 1960s came up with. And largely they just made this stuff up. They did do a little bit of empirical testing, but things when they decided, you know, some of you probably have heard out there in radio land that you're supposed to derate inner traces by 50%. They just made that up. They didn't have the funds for additional testing. They said, hey, you know, this is all tentative data, and somehow somebody in the Army knocked off the tentative part and went from there. So if you're using the IPC 2221 standards to do your estimations, you're wasting a lot of copper. They're really, really far too conservative, much more than they need to be. So IPC 2152 is based off of some empirical data, some empirical testing. But when they did that, they found that internal traces had to be derated, you know, as little as say 5 or 10%. You know, it just kind of depends on what's happening. Anyhow, I found about all of this through the book PCB Trace in Via Currents and Temperatures by Dr. Douglas Brooks and Johannes Adams. And I even talked to Dr. Brooks about this a little bit in researching this webinar. Really nice guy. And if you guys don't want to pay for the IPC 2152 standards, which by the way are still far too conservative than necessarily you need them to be, Dr. Brooks's book is pretty handy, and it talks about traces and vias. And he also made his webinar available on, not his webinar, I'm sorry, a chapter of his book available on his website, ultracad.com. You can just go and download the chapter and read all about this. You know, it is kind of interesting if you're into that sort of thing. Anyways, Brooks and Adams came up with this equation that they approximated. This is based off of the data from IPC 2152. And this is only for external traces, right? This equation, if you're going to, only for external traces at sea level, at 20 degrees Celsius. If you're going to start working in other atmospheres, if you're going to start talking about other temperatures, downhole, space, even high elevations like Denver, this constant, the 215.3, it changes. Okay, so what I'm about to show you is going to be some math that only works for external traces at sea level. If you want something at other environments, other temperatures, other levels, take a look at Dr. Brooks and Dr. Adams' book. And one other thing I want to preface this with, all right, before I show you this chart. You're going to see this chart and you're going to like it. You might even fall in love with it. It might be the most emotional connection with mathematics you've ever had in this lifetime. However, do not just use it willy-nilly. Use it as an estimate only that gets you close to your final answer. If you take this and you make a board and your board catches on fire, I don't want you coming back and saying, well, this one guy on the internet named Mark said it was okay to use. I am not that guy. I could be lying to you right now. You don't know. Anyways, back to the math. All right, so Dr. Brooks and Dr. Adams came up with this equation that the change in temperature of a trace equals this constant times the square of the current. And then they realized that the width and thickness would have different impacts on the cooling. The width gives you greater surface area, more area for convection, more area for cooling. But if you look at that equation, there's not a whole lot of intuitive understanding that comes from it. So what we did over at Advanced Assembly and our sister company, Royal Circuits, is we rearranged it and regraphed it. This might take a couple seconds to sink in, but this equation we moved into this format, right? We solved for width. Now, if you look at the top of the graph, you'll see that we chose an appreciable delta T. Let's say you've got a board and you're going to be operating at the highest temperature you'll ever see is 40 degrees Celsius. And you figure, okay, well, we can go up to 60 safely. By the time we get up to 80, we're going to start decomposing our fiberglass. We don't want to do that. So let's say 20 degrees isn't it's a reasonable amount of temperature increase. So thicknesses, they're going to be kind of a constant too, right? You pull out your copper weight. All right. So we can turn that into a constant too. So each one of these lines is for a constant copper weight. Then all that's left is the relationship between current and width. Greg, you still with me?
Sure am.
Okay, it got quiet. I was wondering if I was talking to myself. I do it all the time. But anyways, so here's how it works for copper weight, right? Let's say that you've got 4-ounce copper, which is pretty heavy copper. And you need to carry 5 amperes of current. Well, with 4-ounce copper, you would need something on the order of, 40 mils trace width. Okay. Well, what if I don't have 4? I've just got like 1/2 ounce that got plated up to 1. Well, in that case, you need something quite a bit thicker. We need something between 1 and 200 mils of thickness. So we've got these charts for you, and we can have them emailed out to you along with the presentation and the recording, in the next couple of days. But for each of these, they just kind of give you an idea of what trace width you need for a given copper thickness and a given current. Is that kind of
Clears a bell.
okay? All right.
No, I think it's a great, with this information right here, as far as trace width goes, I mean, I think this is a really good segue into, as we start to kind of transition into, the actual design and actual fabrication of the bare board. And so, Mark and, everybody out there that's listening too, I want to kind of go over a couple of, kind of key definitions that we are always looking at, whether you're designing with heavy copper or not, but obviously once you start going into the heavy copper realm, they are extremely important. And so typically most fab shops are going to consider heavy copper to be that 1.5 ounce and above. And so usually you're in the 2 to 4 ounce range. Obviously, you can get thicker than that if you want to take 4 ounce and plate it up to 6 ounce, or 4 ounce and plate it up to 5 ounce. I've seen legacy drawings from DoD contracts that take a certain thickness and plate it up significantly, just because at the time that drawing was made, that particular copper clad material didn't even exist. But you still have to go ahead and do it because, well, it takes forever to change prints in the military. So with that being said, I want to cover a couple of different things that are very, very important when designing. And so the first thing I want to talk about is TG, which is basically glass transition temperature. This is what we call the thermodynamic shift of the polymer from rigid to soft. Is essentially when the material of the PCB during the lamination process becomes fluid. Okay. Secondly is what we call the Z-axis expansion. This is actually the physical expansion along the z-axis, which is basically expressed as a percentage of CTE, or the coefficient of thermal expansion. Okay, and so we kind of touched on that a little bit on the via failure slide a few minutes ago. Next thing is what we call TD, which is a decomposition temperature. And Mark kind of talked about this a little bit with the fiberglass. And this is basically the measurement of the weight loss for what we call resin degradation because of the high heat. Next, we look at moisture absorption, which is basically just how well a material can absorb moisture from the environment. And I'll touch on that a little bit more here in a few seconds. And then lastly, we consider another thing called time to delamination, which is essentially the time it takes to delaminate given at a certain temperature. Okay. So when you guys are, starting your process as far as your design, you're going to be looking at an array of materials to choose from. And so you're looking at materials like 85N, FR4, 370HR. These all do well with high heat, just however they're heavy. So if, payload weight is a concern, depending on the application that it's going into, you need to be looking at a Stackup with different material or ways to combat high current, but still being able to provide weight loss as well. There is another material out there that's very difficult to work with. I believe it's an Arlon 85NT, which instead of having a glass weave, it is a aramid fiber. It almost looks like cardboard underneath a microscope. It is extremely lightweight, so it's great for aerospace payload, but it absorbs moisture like a sponge. And so there is a constant pre-vacuuming stages that you have to do pre-baking to rid any type of moisture out of it because it will actually create high resistance shorts with that moisture trapped inside of it.
All right, thanks, Greg. Hey,
Yeah.
we've got a couple Q&As going in.
Sure.
People are salivating over the graphs and slides right now. I knew they would be, Greg. I knew they would be. Don't worry.
You did a great job.
Hey, aren't those sexy? You see how I made the lines thicker for like thicker copper weights, right? Good stuff. Anyways, so we've got a couple questions coming in. People asking for the slides. We'll send those out to all registrants. Don't worry about that, guys. We'll send them to you when we send the recording over. And then we've also got, and maybe you can answer this. I don't particularly know the answer, but somebody said that they don't tend to use ounces per square foot in Europe. I can't imagine why. It must be some of that metric shenanigans. Do you know what measurements they use over there?
I sure don't. Not off the top of my head, no. I could do a little bit of digging and get some clarity back on that, but yeah.
I can Google it too. I understand we're Americans and we do things differently. Sorry about that, Jürgen. But if you send me the units that you used, I might be able to very easily convert these graphs for you.
Sure.
You'd want to double check them, but I mean, if it's just a unit conversion, I can probably take care of that for you. Other questions that I want to remind you of. These graphs are only for exterior traces at standard temperature and pressure. If you're going to use other, you're going to be up at Denver, you're going to be in space, you're going to be in vacuum, whatever. This value, the 215.3, it changes. And the best way to get an understanding of that is, I think, Dr. Brooks' free article at the UltraCAD website, which is what we showed here, right? Read that, at least read that chapter at the very least. Mm-hmm. Okay, so let's move into fabrication. So we're not keeping these fine people for too long.
Yeah, no, absolutely. And so just to kind of pick up where we left off just a second ago, so obviously material selection is going to be your biggest thing to start with. The next thing that you're going to start running into on the heavy copper side with issues is going to be etching and your plating process, okay? And so etching is a process where you're actually removing the copper from the laminate, and this is done either using an anhydrous ammonia etcher or a Cooper chloride etcher. And so at the end of the day, you're using a very, very harsh chemical environment to remove the copper from the clad material. And as fate would have it, if you can imagine it, the thinner your copper, the much easier it is to remove. So if you have tight lines in space, if you have very intricate design work in your inner layer or outer layer artwork, well, as you go heavier in copper, it's going to be much, much more difficult to etch that away. Okay. And so what ends up happening is that you either get an over etch or an under etch. on the inner layer or outer layer. And so on the under etch side of it, you can actually have basically what we call extraneous copper, or a reduction in the spacing that creates a spacing violation between two traces. And so therefore that becomes a violation, becomes scrap. That inner layer would need to be remade, or if it's on the outer layer side of it, you would need to go back and try to re-etch it. On the over etch side of things, this is where you can't really undo this process. If it's over etched, you're essentially taking a nominal line width that you're targeting, and then you're etching it past what its tolerance is. And so it becomes too thin, and then it becomes essentially a scrap piece. So whether it's an inner layer or an outer layer. On the outer layer side, even if you are etching to a certain target tolerance and you hit that tolerance, one thing you need to be very careful with is that if you look at the z-axis of some of these traces, what ends up happening, it looks like a railroad track. And so it basically is too thin, it's wobbly, and it ends up literally completely falling off the laminate. It just rolls itself and it becomes scrap. So the yield on these things from an etching standpoint is extremely difficult. So obviously with yield incurs more cost and it incurs more time. The other thing is plating, okay? And so when you're plating things, you're obviously using an electrical current to pass copper anodes through and plate to the barrel, plate to the outer layer, so on and so forth. And so this takes a lot of time, okay? And so especially when you're using a design or plating a design that is heavy copper, you are constantly pulling out of the tank, pin gauging it, measuring it, cross-sectioning it, making sure that your target plating thickness is correct. Once it's over plated, it's scrap. And then if you're on top of it too, if you're kind of using more of an old school method of DC plating it, you can have a nice range and variation thickness from one quadrant to the next. So if you are really tight on your tolerancing and plating, everything is going to have to be done through rectifiers. And I'm drawing a blank on what do you guys using over at Royal for plating?
The pulse plating?
Pulse plating. Oh my gosh, I'm drawing a blank. Thank you. Pulse
No
plating.
worries.
And so everything is done through programming as far as how much copper to throw. And it's basically programmed to measure total thickness, and it's much more controlled. So it's certainly something to think about with that.
Hey, real quick before we go on, we've got a question that I think some other people might have as well, from David, who wants to know, are there typical minimum trace space for given heavy copper thicknesses? I was going to pull up the chart. Do you think you could talk about that for a second while I do?
I can, I mean, and unfortunately there's, going back to, the graph that you had shared, I think that is a really good reference guide for that. There certainly is going to be, and it's really going to be dependent on the shop that you're using for the fabrication process. Again, like I said, there's different etching processes that are cupric chloride and anhydrous ammonia. Both work the same, but also very differently as well. It also depends on if you're using 1.5 ounce versus 4 ounce or 6 ounce. So as far as specifics, as far as trace and space of really what you're at, I think the slide that you put up is a good reference guide, but really talking to the CAM and the pre-engineering staff at your board shop is a must, especially when you're designing in the heavy copper world.
Because really, when you get your minimum trace and space widths that they give you, they're preferred minimums. They're not absolute minimums.
Sure.
Right? Because that's like, okay, well, if you use these, you're going to get a decent yield. Maybe out of your panel, if you're making 100 boards, 96 of them are going to come out just fine. But if you're willing to live with a lower yield, you can usually get them to push those limits.
Oh, absolutely.
Well beyond what, we were looking at a board when I was up there last time where, God, remember that little thing? It was like 1 mil trace in space.
Yep.
For no good reason other than the engineer didn't know what they were doing.
Right. No, absolutely. Yeah, that's a great point. I mean, and the one thing too that I would totally agree with you is that, these are ideal situations. This is where basically, it can go through. It doesn't have to have, the hand of God on it as it goes through the production floor. It can be basically hands off and be manufactured without any issues. So I mean, if you start, kind of bumping up that etch comp a little bit, what they're going to be doing in the front end and in the cam stages. You can really get, some pretty funky results if you want to get a little aggressive with it. So, I mean, again, every shop out there says, oh, 3 mil line, 3 mil space. Okay, well, yeah, that's great. Everyone and their brother does that. Okay. But, when it comes to, more higher level designs, heavier copper, all that kind of stuff, it's really like, okay, look, I get this is what you can do, in the basic stuff, but this is what I got. What can you really show me? And what can I expect out of it? Because at the same time, it's one thing to push the manufacturability of it, but making sure that your expectations are realistic and in line with that too.
Yeah, absolutely. All right, well, let's get back into it. Give me a second to reset here. Sorry for
You're breaking up a little bit, Mark.
any migraines out there. What's that?
You're breaking up a little bit.
Uh-oh, it says my internet connection is unstable.
So is the world right now. All right.
Well, I like that they used it, instead of just saying, hey, Mark, you're unstable, it's like they tried to give me an out there. That's good.
Makes you feel better.
Yeah. All right.
Good deal.
All right. So maybe you can tell us a little bit about some assembly issues that you see nowadays.
Absolutely. So heavy copper transcends from fab right over to assembly. And so basically with heavy copper is that it conducts heat well, and it's almost a little bit too good. So essentially it acts like a giant heat sink. So what we have to do is oftentimes we'll have to do a pre-bake or a longer pre-soak and the reflow. And then actually before it gets up to its reflow temperature, and then a longer time to actually cool the board. So that is going to be the start of it. Hand soldering, depending on the component and the footprint that it's going on, can be extremely difficult. Once again, it's just extremely quick to dissipate heat. And rework can be an absolute nightmare. Rework can, depending on the copper weight, and I mean, if you got a large back plane, if it's a heavy, thick core plus heavy copper, to be able to get that heat to penetrate, solder to collapse, if you're doing a BGA rework or anything like that, is almost next to impossible. So, realistically, let's start with custom reflow profiles. Generally with leaded and lead-free assembly, there is kind of a sweet spot reflow profile that works on probably 90% of all work out there. Okay. And so if, your assembler saying, oh, we have a special reflow profile just for you, they're probably not, that's probably not really the case, because generally, most designs fit within a certain temperature range and a temperature speed range. So everything collapses, you have your right fillet, you have your right solderability. But heavy copper throws a massive wrench in those gears. And so what happens is, I'm going to take advanced assembly, for example. And so we have 2 Heller ovens. And so the Heller oven has a 9-zone reflow convection, basically. And I consider it to be a glorified pizza oven. And so at the end of the day, you're using software and mechanical heaters and fans to blow hot air or cooler air to be preheating, heating, and then reflowing and then cooling down a board. So if you have, a massive ground plane, large back plane, there is a higher level of attention that is going to be required. And again, it goes back to the yield of it too, because typically there's going to be solder samples and first articles that have to be put through there before we actually run the entire lot. Because at the end of the day, you don't want to put the entire thing through and find out that you got cold solder everywhere or nothing even collapsed. And then you got to do it again and then rework, and then here we are with scrap. All right.
Mm-hmm. Interesting stuff, Greg.
Yeah, it's fun.
Are there any other common issues that you run into with heavy copper?
That's really, I mean, as far as on the assembly side, that's really kind of what we're looking at is, the 3 bullet points that you have put up right there. Hand soldering, like I said, is going to be pretty much non-existent. Selective soldering would be another caveat as far as things being very interesting, because, at the end of the day, If you have a large through-hole connector and you have heavy copper, there's a certain dwell time that needs to be programmed into your machine. And at the end of the day, there's also a certain dwell time of heat transfer that you are allowed to put that nozzle up to there from an IPC standpoint. There needs to be a certain amount of solder fill in the barrel, but at the same time, if it gets too hot, you're going to torch your board. So, those are a very, very fine line. And so this is where it becomes out of the normal scope of work when you're putting something through. So just like on the fabrication side where, a perfect world, everything's 3 mil line and 3 mil space on 1/2 ounce copper or 1/4 ounce copper, on the assembly side, not everything can, fall into it where you can basically, look away while you're running the program through selective solder. This is where it's going to take an experienced technician, a process engineer, testing, evaluation, getting a QA inspection on it, X-ray, to be making sure that not only is there no external damage, but there's no internal damage. You have a proper fill in the hole, it meets your spec, and it's going to be adequate for your program. So,
all right.
yeah.
We're getting some questions in regarding, how we showed the trace and space chart. Remind me to go back to that towards the end. People had questions about that. And from our metrically inclined friends, it looks like the copper thickness is measured in something reasonable, like micrometers, rather than ounces per square foot. So maybe I can take a look at modifying those graphs for them, and hopefully won't make too many mistakes. We do have a question regarding this, and I think I can answer this one unless you want to jump on it. Question from John is, are thermal reliefs around pads where possible better for heavy copper designs? Are there recommended reliefs? So he's talking about these spokes or wagon wheels.
The wagon wheel. Yep, yeah, absolutely. So the thing is that the short answer is yes, but at the same time, what's going to end up happening, and I've seen this 1,000 times, to where if you have 2, 3, 4 ounce copper, and then you have thermals that are on a ground plane, at the end of the day, what's going to happen with those is that those become almost impossible to etch. So they either under etch, so there's basically extraneous copper that fills in where the wagon wheel clearance is, or they get completely filled in because they can't actually etch that small of artwork. So it becomes pointless to even have it there. Okay. I think, Mark, on some of your other design, Gerber designs, I think would be a good point to talk about that. If you want to go to that slide, we can back up to the board stack up. But so guys and gals, if you're looking at this slide right here, to me, this is an ideal way to be looking at something. And so what you're seeing is a design. And if you take a look in the bottom right quadrant, okay, and actually the top right quadrant, rather than a solid ground plane, you see off to the left, you see this crosshatch pattern, okay? And the nice thing about the crosshatch pattern is that it gives you the ability to have heavy copper, but it also frees up a little bit of weight. So you're still getting the actual power and ground functionality of it, but you're reducing weight on it, okay? And it's still acting a little bit more like a thermal from a crosshatch pattern, okay? On the opposite side of that, you're going to see, like, I'm going to call it a quad pack. There's a quad pack that's off to the right where you actually have an entire clearance in white, where if you have a heavy copper design, but you have a very heat sensitive critical component right there, you can still design heavy copper around it, but put an entire clearance relief for that component right there. So again, it's electrically functional, but it's not going to see the dwell, because that heat's going to retain in there. And if that part is critical and is heat sensitive, that heat can't be built up and linger. Okay, so it has to dissipate. So that's another great way, by looking at your on a component by component basis, and being able to still use a higher copper weight design, but still being able to use higher tech components, and not these just old school connectors and through hole components.
Hey, Greg.
Yeah.
Thank you.
You're welcome.
Thank you for falling in love with my design. I was worried when I made this that not many people would appreciate it. I was, but knowing that I have your adulation, it just means the world to me. You know what I'm going to do? I'm going to get one of the Greg Zeraldo commemorative bobbleheads that we're going to produce from this talk, and I'm going to set it on my desk next to that design. That's what I'm going to do, Greg. That's what I'm going to do. Hey, did you want to talk about the symmetric stackups real quick?
I would love to. Yeah, absolutely. And so, when you're doing your stack up, I think this is one thing, and everybody says, oh, no, I wouldn't do that. There's no way I would design a stack up like that. But the reason why we're talking about it is because people do this all the time, right? And so at the end of the day, if you have a stack up, and this is, excuse me, this is just kind of common sense, but if you have an even stack up, even if you have copper or a heavier copper weight, you're going to really reduce your ability, or excuse me, you're really going to reduce, the bow and twist. Okay. And so if you got something that is a tight tolerance, or that's sliding into, that card is, sliding into something else, your bow and twist is insanely critical. I've seen stack ups that have all 4 ounce on one side, and then they have 1 ounce on the other side, and the thing twists like, looks like a Pringle chip. And then, you go and, so you have bow and twist out of lamination, out of the press, and then it goes through etching, and then removes some material that it has even more bow and twist. And then maybe it's a hassle finish, so it goes through a thermal cycle, and then it sees more bow and twist. And then finally you route it, it's out of the panel, is twisted up like a screw, and then you put it on a piece of granite to measure bow and twist on it, and you can put a massive pin through there, and then your customer at the end is saying, what the heck happened to this thing? And it starts with the stack up, and unfortunately it's just going to be the nature of the beast and what happens. So guys and gals, if you're looking at this, making sure that you have your top side match your bottom side, your component side match your solder side on your design, is really going to mitigate any issues with bow and twist. All right.
All right. Hey, we've got a question regarding my design. Apparently not everybody's in love with it. But that's okay, Dan. That's okay. So the question is, when we do this this aperture, this exclusion aperture on the copper, doesn't that create a dip in the board when these layers are laminated together? So
not necessarily.
About, high epoxy prepregs.
Yeah, absolutely. And so, yeah, you took the words right out of my mouth, Mark. I mean, that's if you're not using the appropriate prepreg count, or if you're using the wrong prepreg, that's absolutely going to create some type of a dip in there, and it might be marginal, but I mean, if you're using a 4 ounce copper interlayer, and then you have a clearance like that, and you're using one sheet of prepreg in there, that is absolutely not going to flow into there. There's not going to be enough material when that goes to its soft spot to fill that in. So just as we're talking about even stack ups and everything like that, if you have a relief like that, that is significant, you need to make sure that your stack up is conducive to allow the amount of prepreg in there for that epoxy to flow in there. Absolutely. That's a great question.
All right. So let's move on then into our Q&A. So now we've got time for questions and answers from the community. So if you guys have them, we still have at least 7 minutes, and we'll hang out here for a few more minutes. We're happy to go to the 60 minutes if you guys need us to. We can go beyond whatever we can do for you. Brian brought up, so earlier a question said, do these charts work for pulsed current? And the answer is no, they weren't designed for that. However, if you if you're just doing estimations and, you've got an approximate duty cycle and the duty cycles are not too long, yeah, you could probably just derate accordingly without much trouble. But Brian Pedicolis mentioned that these equations were created by Onderdonk long ago. So I bet you if we Google Onderdonk, we can find an answer to that. All right, here we have our first question for Greg. Greg, are you ready? Are you excited?
I am thrilled.
Greg, you didn't sound thrilled. Greg, sound thrilled.
Let's do it.
Okay, that's what I was looking for, that level of enthusiasm. Question is more solder paste required when using high copper thicknesses?
Okay, so yes and no. And it's really going to depend on what happened, or excuse me, it's really going to depend on what component you're placing, okay? And so I'm going to throw this out there just because I work for Advanced Assembly, okay? So we have the luxury of having a solder paste printer, okay? We don't use solder stencils. So if you have a high copper heavy copper design, and you have BGAs, but then you also have your basic passives and all those fun things and everything. We have the ability to control the amount of solder paste deposit on the BGA, and then we can increase the solder paste deposit or the actual design of the solder paste application if it's on a larger passive that would need more solder, okay? Because at the end of the day, if I apply more solder to a BGA, I'm setting myself up for a rework nightmare with shorts and bridges underneath that. As soon as I go to X-ray, it's going to look like it's going to be a mess. Okay, so for the folks in the assembly houses that are using stencils, well, guess what? It's one stencil, and you're going to get the same solder deposit on the BGA as you are in your 0402 passives. Okay, but with what I'm able to do is put that in essentially control that by using the amount of deposit. So yes, the short answer to that is depending on the component and the footprint, yes, you would. But how your assembly house controls that needs to be discussed.
Okay. We've also got questions. I do need to go back to the trace and space Stackup here because I know we had questions about that.
Yeah.
But we had a question about via clusters I wanted to tackle. So let me bring up that, and then we're letting people look at that. I'll do the via clusters. So the question is, what can you tell me about via clusters to transfer current from layers to other layers, and do they help with heat transfer? So Tom, I want to refer you back to that book that I presented earlier by Drs. Adams and Brooks. And they have a whole chapter on vias. And it turns out that the via aspect ratio, if you're just doing like a single via, that the temperature of the via is mediated by the temperature of the traces that it's connected to, more so than anything else. So the aspect ratio, the copper plating, all of that they found didn't matter nearly as much as you might think. Now, that being said, I still would personally, I would use more than one via for a high current trace, because as you saw earlier, the varying coefficients of thermal expansion can cause the via wall failure. If you have more via walls, there's less opportunity for failure. So I wouldn't use them necessarily from a thermal standpoint, but I would certainly use them from a reliability standpoint. We've got people asking for the slides. We will absolutely share those with you as well. All right, so coming back to this, and if you guys had any questions regarding this that we dismissed and you want to ask them again, please feel free to. But the inner and outer trace and space widths vary because of the way that the boards are fabricated. We don't typically plate internal layers of the printed circuit board, right? If you want 2-ounce copper, if you want 4-ounce copper, we'll just walk over to the shelves and we'll pull off the 2-ounce or the 4-ounce copper if we can, right? If it's sitting there, we're going to use it. It takes less time. It's more reliable. Platings can delaminate. So if we've got it, we're just going to go use it. Outer layers is different. On outer layers, we have to plate because we have to form your vias. That's how vias are. I mean, vias aren't these little cylinders we punch into your board. They're formed in an electrochemical bath. So we can mask, and we've actually, by the way, we've got a whole thing on vias, a whole presentation on vias if you guys wanted to. But anyways, we can put on a layer of mask, and we can electroplate, and we can build up the heavy copper traces on the exterior layers. Then we can come behind and we can etch down in another process. So on the exterior layers, we can squeeze out a little bit more because we don't have to have as much etch back compensation. Greg, I don't feel like I explained that well. Do you want to try to clean that up for me?
No, what was the question again?
Sure. So why do we have different trace and space on inner and outer layers?
No, I think you hit the nail on the head pretty closely with that. I mean, it's like you said, very rarely have I ever seen, and I have, but it's very rare to where you're going to have a piece of interlayer material that you're going to take that base laminate and actually plate it up. Okay. It's just typically it's much easier to etch comp your inner layers than it is your outer layers, because on your outer layers you're playing with plating, and plating is the variable to all of these things, because unless it's in a controlled environment like a pulse tank, it's all done through DC. And as old school as that is, it's a great way to plate and everything. But when you're in the heavy copper world, it is very, very difficult to control that once it gets to a certain point. So no, I would agree with that.
All right, so we've got a question, and Peter asks, are there any considerations to be mindful during design connector landings with increased weights? They seem more mechanical stress.
Mm-hmm.
So heavy copper with off-board connectors or other such things, are there any design considerations you're aware of?
Not specifically, and I mean, and you can talk about, and I don't want to call it bussing. We kind of glazed over that a little bit. I know that we do have a slide for a little bit of content on that, but at the end of the day, if you have a connector that's going on, if you have a heavy connector that's going into heavy copper, you need to understand that there needs to be enough material inside the board to be able to handle that heat transfer. You can't have a thin heavy board that's getting a heavy connector and expected to go through a selective solder process or a wave solder process, and it to either one have full solder or two not scorch the board. You can't really have your cake and eat it too. You know what I mean? So being mindful of that is all about how that material is going to be able to absorb and how the copper is going to transfer that heat.
All right. Question from Brian Pedicolis. What is the maximum practical plating thickness for outer layers? It's just shown here as up to 6 ounces on the thing. What's the maximum practical plating thickness, Greg?
Realistically, I would stay in the 3 to 4 ounce range. As far as actual thicknesses of plating or actual weights of copper, I would assume that it's plating thickness. I don't know the answer.
I think what we have is a variety of people from around the world, it seems, that measured in different units.
Sure.
So maybe just talk about it in terms of weight.
Yeah, I mean, as far as the weight goes, the 3 to 4 ounce on as far as copper goes is really a controllable and etchable and workable thickness. Okay. As far as, thousandths of an inch that are plated off the surface and everything like that, I would probably want to get a little bit more concrete data to support any type of answers as far as, what the specifics of that are, whether that's in millimeters or thousandths of an inch. But, at the end of the day, it's just logical. The heavier copper you go, the harder it is for that etchant to go through it, the harder it is to control your line and space. If you have critical design that it includes, say, controlled impedance, for example, the likelihood of actually hitting your target impedance readings is going to be, I don't want to say next to impossible, but it's going to be very difficult to achieve. And so just watching the etching process and making sure that you're able to remove the material to get to the target impedance on these things, you start getting too thick and it's going to be a pain in the neck. I mean, there's no other way to call it that. And the one thing I wanted to touch on too is that, heavy copper it has its place and has its reasons for why people design with it. Okay, that's why obviously they make heavy copper weight inner layers. That's why we talk about and have these webinars and everything like that. But you need to think about it though, because I'm going to be honest, you need to make sure that this is really what you need. Is there a reason specifically why you need heavy copper? And I think a lot of times, and just designers that I've worked with, it's really kind of just a flex on other designers of saying, hey, look, yeah, mine's, been designed with heavy copper. It's got this aspect ratio. It's got yada, 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 and all these things. And so it's more of just a personal accomplishment to do it rather than actually suiting the need of what it's going into. So I really want you guys and gals to be mindful of, understanding your product, what it's going into, what its lifespan is, and is this really what you guys need? And I think it's just an honest question to kind of get the elephant out of the room too, because too often I've seen people, it's like, well, I'm not really sure why I designed it like this. I just did. Or I had, a colleague with this company do this, and I wanted to kind of borrow some of their ideas and use this. And it doesn't, heavy copper doesn't transcend industry. Let's just put it that way. So be mindful of what you're actually designing it into. Okay.
Something else I would like to add too, out in heavy copper land, I can't tell you how many times people have, said, oh my God, 6-ounce copper, I can't afford it, blah, blah, blah. It's a 4-layer board. It's a 4-layer board. Okay, well, you got 4 layers. Why don't you just run 1.5 ounce on each layer? It's not heavy copper. It's cheap. Just do that. They're like, you can do that? It's like, yeah, you can do that. You can spread the current between layers. Mm-hmm. So instead of having 6 ounces on your exterior layers and 1/2 ounce in the middle,
yeah,
split it. 3 ounces on everything, 1.5 ounce on everything, and life becomes so much simpler. So, Brian, I hope that answers your question. We've got a question from Jacob. During the assembly process, when going through the oven and using heavier copper weights, how does this affect the process? Is there enhanced risk of damaging components with the heat up and cool down process? So it seems like Jacob is imagining the convection reflow ovens. Did we touch on vapor phase reflow?
No, we didn't. We didn't talk about vapor phase at all. But I mean, realistically, I mean, if you're talking about if you're talking about reflow as a whole, it absolutely increases the risk of, just melting components. There's a certain threshold where, that component was designed to operate and be reflowed in X temperature. And these are all listed on the component data sheets that you get from DigiKey or Mauser or anything. And so, if you're designing a board and the solder paste and is all there and the components placed, and at the end of the day, your board, again, is a giant heat sink and is just robbing all of this thermal mass from it, and it can't actually properly wet the pad, reflow, and cool, you're either going to damage the component or you're going to have a poor solder joint. Again, this is where you really start to float the line of manufacturability if you start going into the netherworld of heavy copper. And like I said, the reason why we're talking about this is because we see this regularly. It's not like this one time, 10 years ago, we saw one design that came through here. This is something that we deal with on I don't want to say a daily basis, but easily a weekly basis, I think, on the fab and the assembly side of these things.
Yeah. So vapor phase reflow, Jacob, is really kind of a cool technology. You use a chemical whose basically it's got a temperature, a transition temperature between the liquid and the solid phases that's just a hair, like 5-10 degrees at most, degrees Celsius above the temperature that the solder transitions from a solid to a liquid phase. And when you transition, during that time, the temperature of a substance remains constant. And it has essentially an infinite heat capacity. So you can drop your board in, your heavy copper board, and it will just sit there and suck up all the heat that it needs, to melt that solder. Unfortunately, then it can linger in the board, and you're kind of out of luck too. But it's certainly something to look at. All right. A question from David: what's the cost difference between heavy copper weights? Is one more popular and therefore cheaper? I'll let Greg answer this, but David, it's not much. Depending on what thickness you want, if you want to go to, 1.5 ounce over 1 ounce, you're probably barely going to notice the cost increase. Greg, can you narrow it down any more than that?
Yeah, so and I'm not going to be able to give you an actual like dollar per se, but really and I would agree with that. The delta that you're going to see in the raw materials, as far as the 1.5 to 2 ounce, 2 ounce to 3 ounce, 2 ounce to 3 ounce, etc. It's not anything that's going to bowl you over in your chair or anything like that. Where you're going to see your cost increase is on the actual cycle time and resources needed to ensure that your job is going to be through the process. Okay, so you're looking at your manufacturing cost is going to be higher, but your cost of raw materials and everything, the delta between those is not really going to be that significant.
All right. Well, with that, I would very much like to thank you. I would like to thank everybody for joining us today. This was not the webinar we intended to give. So some of you might have signed up and come to something else. That's because we wanted to leave our factories. They're producing some ventilator parts right now. We didn't want to take those engineers off the job. So I really want to thank Greg for stepping up. He's known he was giving this webinar for a little over 24 hours. It was great. Thanks for stepping in, Greg.
Yeah, anytime. That was fun.
Yeah, if you have any questions for Greg Zeraldo, if you'd like to buy a Greg Zeraldo live action figure with karate chop action, if you want the Greg Zeraldo bobblehead or Greg Zeraldo t-shirt, just visit gzeraldo@aapcb.com. Our next webinar is going to be using augmented reality, some new technology called Inspect AR that uses your cell phone or computer camera to look at and help you debug, inspect, and work on boards remotely. So if anybody has some interest in that, we've got some information up at our website, and also in the same emails that you're getting from us, we'll be sure to click that into you too. As soon as this recording is available, we will send it out to you. It usually takes a few hours to process and trim down and whatever. We'll send that out to you. I'll send that out to you with graphics as well. After that, I will look into what it takes to modify those graphics for our European and Asian friends who joined us today. It was the first time that I think we were aware we had an international audience, so it's never even really been a consideration before. I really appreciate you guys joining us. If you have any further questions, please direct them to gzeraldo@aapcb.com or give Greg a call. There's usually, I have to tell you, there's usually a line of people waiting to talk to him, though it's like 40,000 people deep. I mean, you're going to be on the phone for a while, a long while. But I mean, Greg, any closing comments?
No, I just want to thank everybody. Thank you, Mark. Thank you, Lisa, for getting it set up. You know, if you guys have any assembly-related questions, fab-related questions, myself, I'd be more than happy to farm those out and get you what you need. Thanks for your time, everybody.
All right. Thank you. Have a good day, everyone. Be safe.